All righty. So the votes are in. It was about 3-1 saying do the same thing on Thursday as on Tuesday. So if you were in the 1, not the 3, well, sorry about that, but that's what we'll go with. And okay, so any questions on anything right now? Yeah, that's usually the case. Okay, but questions are good, so never be afraid to ask questions. So, all right, well, we are looking at Chapter 3, and what I found on Tuesday was I really only had time to get into the single proportion stuff as far as introduction on things. I'll be adding some videos, all that kind of stuff, but they're not there right at the moment. So 3.1, what we're doing in this particular chapter is we're really getting into that question of hypothesis testing and using that as a tool. And so we're beginning just with proportions. So everything's count data. Okay, and that's in your project. You have the thing about chi-square and how you might be able to use chi-square with your particular project, final project, and so as we look at these, what I'm trying to get you to realize is we keep asking the same question over and over again. We're just really doing it with different types of data. And there are some nice things about the chi-square when we get to that, and really count data in general, is we don't have to worry as much about whether we are pulling from a normal distribution population when we take the data. Now we're still using a normal distribution to estimate our answers, but that's different than the idea of pulling from a normal population to begin with. Okay, so one thing I do want to point out, because at least right at this spot in the text and I differ, but there are other spots where we don't, which is kind of weird. I think the text is really a very good text, and the authors are very good about how they approach things and all that. But it is kind of weird because they really, for the same stuff, there are a few different places in the book where they give different answers. And so here is one of those cases. When they say, well, when can you use the type of stuff we're doing in chapter 3, and they say, well, if when you look at your proportions in your data, if you can take your sample size times the proportion of successes and get at least 10, or your sample size times your number of failures, because really it's symmetric. Again, that's a big deal here, is that a failure and a success, those are just names. Okay, so a success can be that a person has cancer. Okay, generally when you're having a conversation with somebody, you don't go, oh wow, congratulations, you have cancer. Right? That's not a success. However, in the world of probability and statistics, a success is simply the thing you're counting. And so if you're counting the number of patients in a study who end up developing cancer, then that was a success. And so the idea there, though, is that successes and failures are really interchangeable. They're really in the name. And so we could count successes, we could count failures. It actually doesn't really matter. And so that's why we have this symmetry that this n times p, okay, that's my expected number of successes. So, if I sample from if I take in a sample size of 20 and I expect p to be a 1/4, then my expected number of successes is 5, because that's 1/4 of 20. Okay, so that's just n times p. And my expected number of failures in that case would be 15, or it's just the 20 minus 5 is another way to look at it. And but both of those, they're saying, have to be at least 10. Okay, well, actually, in other places in the text, they say 5, not 10. Generally speaking, if you look at a chi-square suggestions, they say, at least 5. Okay, everything should be at least 5. And so I wanted to point that out, that they use 10 here, but actually if I looked enough, it's somewhere else in the text they use 5. Here, in this one, they don't mention n at all as far as sample size. How big a sample does it need to be? And here, I guess if p was a half, we could get away with a sample size of 20. In another spot in the text, though, they say it needs to be at least 30. So they, for whatever reason, they, I don't know what's happened here, if maybe different authors in the group did different sections and they didn't check each other that well, but they have some different answers. Okay, we're going with at least 5 and a sample of at least 20. And just to kind of show you why, is that the right thing? No, that is the right thing. So here I am showing a normal distribution and a binomial distribution. The binomial distribution is what's really happening when you are sampling success-failure kinds of things. So the binomial are the circles, and the continuous line is the normal distribution. And you can see how well they line up. Okay, and in that case, if you look over on the left, n is 20 and p is 0.5. So when you take n times p, you get 10. However, if I take this down to 0.25, then my expected number of successes is 5 down here. And now it doesn't fit quite as well, but actually it fits pretty darn well. I mean, those dots are pretty close to the blue curve. And actually what's going on is you draw a bar graph for the binomial stuff and a histogram for the other, and for the normal. And you would see they don't actually quite match up if you look at the probabilities, but they're really not bad. And things like this where it's a little bit to the one side, actually that's not necessarily a bad thing, okay? Because again, of the way you're approximating things. But it really doesn't look too bad there with n equal 20 and my product being 5. And just to show you, if I take this up to 0.75, what that's doing is it's just sort of the opposite picture, because now what used to be a success is now a failure, and what used to be a failure is now a success. But that's just to show that the numbers really aren't bad at if you have at least 20 and you ask that the expected number of successes and failures are each at least 5. Okay, so I wanted to toss that in since the book has the different items there. Yeah, okay. So, all right, well, we'll go back here. Okie doke. So with that, in 3.1, we want to do a couple things with proportions, and these are just point estimate kinds of things. So I go out, I take some data, right? I take 25 observations, and have maybe we'll say 15 successes, whatever that means. Okay, then my p hat, my observed proportion of successes, so my data, we usually go with a hat on it. My p hat is 15 over 25, or what is that? That is 3/5, so 0.6. So we get 0.6. Now, if you're going out and looking at things, well, is it really 0.6? I don't know, right? Maybe it's 0.58, maybe it's 0.71, that kind of thing. And so what we want to do is get an estimate of, well, how good is that number given this data? I realize the real number might not be 0.6, but where do I think it is? Okay, and that's this confidence interval idea, and we looked at confidence intervals, what was that, back in chapter 1, I think, it was confidence intervals. So that was module 2. We looked at just this idea of a confidence interval. Well, here, with these proportions, the way we will create it is we're going to approximate our population distribution of this proportion with a normal distribution. Okay, so what we need then is a standard deviation on this. Okay, because remember a confidence interval, so for a confidence interval, on a mean, or for a mean, okay, and a proportion is a mean, because see, I added a bunch of things up, the successes, and divided by how many times I did stuff, right? It's a mean, it's an average. And so my confidence interval is the mean, so you could put x bar for a mean. I'll rewrite it with a p in there, but x bar, and then plus or minus the number of standard deviations I want, and you can kind of think of it as the rule of thumb idea, right? How much of the population is between, plus or minus 1 standard deviation, 1.5 standard deviations, 2 standard deviations, that kind of thing. And we call that number z alpha over 2. How many standard deviations do we want? This many. Okay, and it's all one symbol, z alpha over 2. And then times our standard error. Okay, now ours is going to change slightly in the way you would write it because, well, we're talking about proportions, and so I would use a p hat. Okay, so same idea. This is an average again. So I could just use that, but we're talking about proportions, so I'll use a p. Now, the z alpha over 2, the alpha part, we should be getting, we should be starting to get an idea of that alpha. Okay, usually for us, okay, and when we talk about confidence intervals, we sort of switch it. Instead of saying, alpha equal 0.05, we talk about the 1 minus alpha confidence interval. Okay, so typically, we're going to talk about the 1 minus 0.05 or 95% confidence interval. Now, you can have a 90% confidence interval, you can have an 80%, you can have a 99% confidence interval. You can have whatever you want, but typically, we're going to go with 95%. And 95% of the population, how many standard deviations? Plus or minus how many standard deviations to get 95% of the population? Yes, peace. 2. Okay, so it's about 2. The actual number, right, this z alpha over 2 is 1.96. Okay, so for this, z, and I could write it as 0.05 over 2. Now, you could also write z 0.025. And I guess I've seen it that way, but usually you kind of keep it this way to keep the idea of what's going on. And now why over 2? Because we're taking the middle. So half of our 0.05 is on the right and half is on the left. So this is 1.96. Okay, if I wanted 99%, I would be out there closer to the number 3. And if I wanted an 80% confidence interval, I'd be in closer to the number 1. Okay, those are just based on rule of thumb things. But I could look them up. If I Google, it'll tell me what these numbers are. But for a 95% confidence interval, I want close to 2 standard deviations or 2 standard errors on each side. Okay, so that's what we do there. And now, I know p hat, it's right there. I now know my number of standard deviations I want, 1.96, but I don't know my standard error or standard deviation. That I don't know. And in this case, what we do, and this is based on a binomial distribution, and its standard deviation, it's just the square root of our p hat times 1 minus p hat, all divided by n. So in this case, we would have the square root of 0.6 times 1 minus 0.6, all divided by, what did I say, 25? So 25. And I have no idea what that is, but I can go to something like a spreadsheet, or in my case, since I have Desmos up here also, along with this other one, I can just put it in here and say, square root of 0.6 times 1 minus 0.6, and then all divided by 25. And turns out to be really close to 0.1, but 0.098. We'll go with 979. And there's my standard error. Okay, and then from that, I'll go back here for a moment. Okay, so I have my 0.8 up there, or 0.098, whatever that is. Yes, that was what it was. So now, this says my 95% confidence interval is that 0.6 plus or minus 1.96 times 0.098. Now, what's kind of nice here is this is about 0.1 and this is about 2. So really, what I can do pretty quickly is just go with, 2 times 0.1 is 0.2. My 95% confidence interval says the real mean or the real proportion is likely between 0.4 and 0.8. Okay, subtract 0.2, add 0.2, and get that. Now, so I can get the actual number, and let's see, I gotta go back here. Now, so I want to calculate that 1.96 times the 0.098. I want to call it something. I'm going to call it ME, like that, because it's all about me. No, that's not why. ME, because I'm calculating what we call the margin of error. It's political season. You've probably heard that, right? Margin of error. We took a poll. 72% of Americans believe, I don't know, we should chew Trident gum or something like that, right? With a margin of error of, and that's just the half the width of our confidence interval. That's what a margin of error is. And so this equals, and I should probably go up here and call that S, so I don't have to retype that. And then, so this is 1.96 times S, and we get our margin of error is almost 0.2, 0.19. And so then I could create my lower bound, I'll call it L, is equal to 0.6 minus the margin of error. And it's a little more than 0.4. And then my upper bound is 0.6 plus my margin of error, and almost 0.8. So I can get those that way. So like I said, about 0.4 and 0.8, we'll call them 0.41 and 0.79. And so I don't remember what that was, but we end up with an interval of 0.41. I can fill it in to make it work, and up to 0.79. So I guess that was 0.19. And there we have it. That's a confidence interval for a proportion. The only thing that would change about all this is simply, what confidence do you want? Well, since everything else we seem to base on alpha equal 0.05, why not this, right? So usually we would care about 95% confidence interval. Again, I think the big thing to remember about confidence intervals is if I want more confidence, so if I want a 99% confidence interval, I need a wider interval. Right? Think about it as hitting a target. Right? If I want to be really sure I hit the target, make it a really big target. Right? Pretty simple. Archery? Yeah, you're archery, right? Yeah, so, so it's pretty simple. Right? If I want to hit the target, make it a big target. So 99% confident that I'll hit it, make it wider. 60% confidence that I'll hit it, then make it smaller. Okay, but that's confidence intervals. And that I would like you to remember and know and get a feel for. But that's the interesting thing in these, in polls and so forth, when they mention it, they say, well, with a margin of error of, well, great, but what's it based on? In other words, so the margin of error, they're taking a standard error multiplied by a certain confidence. Oh, well, it matters a lot, plus or minus 3 percentage points. Well, yeah, but is that a 99% confidence? Is that an 80% confidence? It matters. Okay, so usually you don't get that reported. And to tell you the truth, I'm not sure what they usually use. If they, I would think they probably use 95% confidence intervals, but I don't really know. Any questions so far on anything? As I'm erasing it? We can always look back at the video, but No? Okay. All right. So that's what we're doing with the confidence intervals for the proportions. Now, then, of course, what we want to start getting into is the idea of a hypothesis test. And now, it's a little different with confidence intervals than it is with means. So when we get into numerical data and we take real averages that we think about as averages, the similarity between a confidence interval and a hypothesis test are actually really close. I mean, they are pretty much dead on the same thing. Hypothesis test here compared to the confidence interval, hypothesis test is, it's a different perspective of same thing, but not quite as close as with regular means. And the difference is the standard error. When we compute a standard error for a confidence interval, we're going to use our data. When we compute a standard error for a hypothesis test, we're going to use the hypothesized proportion. Now, that only makes sense because in a hypothesis test, we are assuming the null hypothesis. We're assuming that whatever we say for the null hypothesis or the hypothesized proportion is what's going on. So of course we would use that. It is the assumption for a hypothesis test. Well, here with a confidence interval, I don't have a hypothesized proportion. So I don't have one to use. This is the best I can come up with. Okay, so in that way, they can be slightly different. But here's kind of what's going on with, and I think I've drawn this picture before, I'm pretty sure back in chapter 1. So here is, say, P0. That's what's hypothesized. Here's your data, P hat. Now, if we computed the standard error exactly the same way in both cases, what you would have is that in a confidence interval, we're saying, okay, here's our mean, or here's the center of our distribution, and that distribution looks like that. Okay, it's a normal distribution that looks like that. And we're going to draw our confidence interval at 95% of the population, centered. Okay, because I could put the 95 in one direction or the other, but we're going to center it. And so maybe that happens to be there. Okay, so here's my confidence interval. Well, so the hypothesis test, if it had exactly the same standard error, it would take this same curve up here, the dotted line curve. Now I'm going to do it as a solid line this time. And it would draw it this way, but it's the same curve. We've just picked it up off the chalkboard and set it down over there. In a hypothesis test, we're saying the center is here, and we're asking, does P hat land within the 95% area or not? And here's the thing, if this P0 is outside of my confidence interval for that P hat, then that P hat is outside of my hypothesis interval or my null hypothesis acceptance area for that P0. This P hat will be outside of it. So, you know, if I had something that looked like that, then my rejection region is going to be, in this case, actually, maybe I should make those dotted lines to go with the dotted distribution. And then here, I would have similar things for the hypothesis test. And those, it's just an optical illusion. That's actually the same distance as that. Really. It's just, it's because, I don't know, you need glasses or something. So, so this is the same thing, but if, you know, if our confidence interval would have included our P0, then our P0 would have included the data, the P hat. Okay, they're really the same thing. It's just where am I centering the population as I think about it. Now, because of the slight difference in the standard error, it is actually possible that I could create a situation where I might reject the null hypothesis if I was doing a hypothesis test, but the null hypothesis proportion, the P0, could actually still be in the confidence interval of my data, or vice versa. Could happen, not real likely, but it could happen. And that's because, as we will see, when I calculate the standard error, I use a slightly different value here. So let's get on to doing that standard error. I'm going to leave that up there and go ahead and get rid of this picture here. Well, actually, I can get rid of this stuff too. Okay, so suppose we still had that same data, but our initial hypothesis, H0, was, we were expecting, well, not necessarily expecting, but our null hypothesis was something like we talked about before, maybe just that whatever we were sampling from, we were going to make a null hypothesis that the population was 50-50. Okay, like we did the other day with majors and number of females in the various majors, right, or proportion of females in the various majors. So here, suppose we said, well, we think that P is equal to 0.5. And then our alternate would be that P is not equal to 0.5. And so now, suppose then our data, n equals 25, and p hat was our 0.6. Okay, so same data, same idea. We sampled something 25 times, got 60% successes or 15 successes, and so there's our data. Now we would like to decide, okay, which of these two hypotheses do we want? And, in the end, all we have to do is calculate a p-value. Okay, well, calculating the p-value. So now I'll get rid of this. Okay, for the most part, to calculate a p-value our old way, without technology or something, we would have had to turn it into a standard normal distribution. Okay, we'd have had to look at it that way. Well, to do that, we need a standard error. Okay, standard error. Yeah, same idea. Square root P0, though, 1 minus P0 over n. So in our case, we have 0.5, 1 minus 0.5 over 25. And now we'll see we get a slightly different number than this one. And so if we're doing a hypothesis test, so I'm going to just go in here and call that 0.5 and that one 0.5. And so what we see is now our standard error is 0.1. So this is equal to 0.1. Little bit different than the other one there. So go back here, I think. Yeah, if the noise I'm hearing, if it's bothering anybody, you can always shut that door. So, but so you see, almost exactly the same. I mean, they are really close, but they're not the same. And that's why you could get this weird situation that the confidence interval is actually a slightly different size than your, well, outside the confidence interval, I guess, is a slightly different size than your rejection region. They're maybe not quite the same thing. But they're pretty close. Okay, so you can pretty much say, hey, if we end up rejecting rejecting this hypothesis, that meant P0 wasn't in our confidence interval. Okay, but remember, our confidence interval went from around 0.41 up to 0.79. That's inside there. Okay, that's in my confidence interval for my data. So I'm really sure it's very much in there. I mean, it's way inside it. So I am really sure that I will fail to reject the null hypothesis. Okay, I'm going to stick with this. Okay, I'm really sure I'm going to get a big p-value, way bigger than 0.05. Okay, and I just know that from the work with the confidence interval and how big that was. Okay, it contained 0.5 in it really well. So, to get my normal distribution number, I need my standard error. Right? Generally speaking, my z, okay, my standard normal number, is my p hat minus my p0 divided by the standard error. And again, all you're doing is you're turning this difference here, the difference between my data and my hypothesis, we're turning that difference into the number of standard errors. And that's all we're doing. I mean, this formula is not that deep that way. Right? You know, I'm just finding that difference and then asking, well, how many standard errors is that? So in this case, right, p hat was 0.6, my p0 was 0.5, and standard error was 0.1, and you get 1. I could do that one in my head, right? Because the difference was 0.1, the standard error was 0.1. Oh yeah, I was 1 standard error away. And then my p-value, I would have to look this up. My p-value is equal to 2. Now, the 2 is because I have a two-sided hypothesis. And I have to look this up in a table. What's the probability that a standard normal variable is bigger than 1? Well, actually, I know what that is. Okay, because I know the rule of thumb. Well, I don't know it exactly, but I know the rule of thumb. Right? In between plus or minus 1 standard deviation is 68% of the data. Okay, so as I look at this, okay, I might have to draw it in order to know it, but what I know is going on is here's 1, there's 0. Whoops. I know that that's half of it. And I know that between minus 1 and 1 is 68%. So half of that is 34%. So that's 0.34. So I know to be out here is 0.16 to add up to either, I can think of it as adding these two adding up to the 0.5 or the 0.84 and that adding up to 1. Okay, so I know that this is about 0.16, so I'll do approximately 2 times 0.16, and then that's equal to 0.32, way bigger than 0.05. And so I failed to reject the null hypothesis because my p-value is way bigger than 0.05. Now, you are actually welcome. I don't think I'm going to really probably test you at all on quizzes about doing all this. You can do things this way, but one of the tools I give you is so I got to go in here somewhere and go to module 4, and then I guess was it under instructional content, I think. Yeah, so probably the one you'd use the most. Now, I actually included this in here. I'm not sure that was a good idea, but there's also a link to it. So we'll have to wait a second there. It opens it up. So here's a template that you can actually use right here and perform a hypothesis test, and it gives you a nice picture. Now, you don't have to use it. You could go to Excel. You could do it by hand using a calculator, all that kind of thing. But, here to use this, right, we said P0 was 0.5. We said we had 15 successes, and so that meant 10 failures. That's just the way this is set up, number of successes and failures. Now, it doesn't do the addition for us. I don't know why I didn't have the do it, but anyway. So N was 25, and so p-hat, it calculates that, and it calculates the p-value. I said 0.32 using the rule of thumb. It's actually 0.317. Pretty close rule of thumb, right? I mean, if you got the right numbers, it's pretty simple. Now, what this picture is showing you is the dotted lines are where we decide to reject. If all of our area, and I don't remember if the orange or the green, oh, it'd be the green because we were above. So the green is that probability, that 16% is that green. But what it's showing is the data, so there's the data at 0.6 and everything to the right of it. And so that is everything that sort of fits our data, right? We got 0.6 or more in this hypothesis test. And then since it's a two-sided, it also did this orange stuff down here, or red, whatever. No, it's orange up there. Orange stuff is the symmetry part. It's the other side of it. So it shows us a picture of what we're calculating, and we have just calculated those two areas together at about 32%, okay, or 0.317 here. But then the dotted lines are at the 0.05 spot. Now, so I could play with this a little bit and, try to, what if we had 20 successes and 5 failures? In that case, oh wow, it really made a small p-value, really tiny. So, I didn't want to do anything quite that drastic, I guess. So maybe 17 and 8. And there you see I'm getting really close. That's getting very, very close to being right at the 0.05 line. And if you look at the probability it generated, it's 0.07. And so the areas in the dotted line are starting to match up on the edges. And if I could pick exactly the right numbers to make 0.05, they would line up right at those edges. But, so it's a visual of what we're calculating. Okay, we're calculating those probabilities based on that normal distribution. And so I think working with this template is probably not a bad idea to help you gain some intuition as to what these numbers are actually doing as far as a picture. Okay? All right, well, so we're definitely out of time. So I will see you next Thursday. And yeah, if you have any questions, certainly send me email, something like that.
I'm sorry I was late to class. I actually got rear-ended.